All right, should be good. Yeah, so we're just gonna look at some homework problems, right? So which ones were people struggling with? Six through nine. Okay, nice. All right, we can talk about those then. Let me bring this up real quick. Okay. So 6. Yeah, this one. This one, and this one. All right, let's start with number 7 here because I did actually just do this in recitation not too long ago. So we'll look at this one. Can you guys see the document all right? Yeah, we can jump to number 1 real quick too. So there's like this thing that's going on. For instance, like if I type an equation, is it clear that that is an equal sign, or does it? Because it looks good on my display here, but is that obvious? Like I said, that it's an equal sign, or does it look like a minus to some people? Okay, cool. I'll zoom in a bit more though, and then we can do this. All right, so let's just put down what we have. We have the mass of the ball is 5.0. So yeah, that must only be happening on my school computer then, which is something I'll have to look into. We have the length of the chord, right? We have the velocity, the tangential velocity here, which is 4.09 meters per second, or I should say the tangential speed. And we need to figure out what this angle is and what the tension is. So let's see here. All right, the first thing is to, of course, specify my axes, right? So what do I want to do for that? Like, how do I want to make my x and y axes? Or I should say, kind of suggestively, my centripetal and y axes. What are we thinking? Anybody? I mean, like, okay, here's the thing, right? I think I said this to a few of my recitations today. Like, I'm, of course, willing to help you guys with this stuff, but, like, I do need a little bit of input from you because otherwise it's kind of like I'm just doing your homework for you, right? Which is, which might sound great to you, but it's kind of not what we're going for here. So can somebody tell me what I should do for my axes? Yeah, no. So I mean, like, remember that when we work with Newton's laws, right? And this is a Newton's second law problem, is that we want to first just define our axes. Okay, those are the forces, but like, what are my x and y directions here? Or I should say, like, my centripetal and y directions. Like, how would those look? Yeah, okay, that's good. I like that. So we could say y is positive up and x is inward to the left. So that's good. So this is what we'll do. I'll just draw like some thin lines here to indicate those because this is something we need to do for every problem that we basically do with Newton's laws. So that's like my y-axis. This is my x or centripetal axis. Okay. Cool. So what are the forces on this thing, right? Somebody already said, so we'll just go with that. there is the gravitational force, which is going to be pointing straight down. And then there's going to be the tension force, right, which should be directed along the rope. And that's it. Like this. Now, if what we want is we want to solve for this angle here, then we can just note, right, that because geometry, this angle is the same. And so this will be my reference angle. I'll just label these. This is T, and this is mg. Okay, so I will sum the forces in the y direction because that's probably something we're comfortable with at this point. And so I'm going to say the forces in the y direction will just be the y component of the tension, right? Which is actually going to correspond to cosine of theta in this case. So T cosine theta minus mg, right? Because the gravitational force is already completely aligned in the negative y direction. And we set this equal to 0. Because we're going to assume that this is all kind of unfolding such that the ball is at a constant height above the ground, right? Now, just so we're clear, right, what's happening here is this thing is moving in a circle around the pole. So its path, right, is going to kind of look like this around the pole. Okay, so then how about the centripetal direction then? What is my net force there? And we'll just say the x direction because, right, we can identify the x direction or the negative x direction as we usually think about it as the centripetal direction. What am I going to put here? Like, what is my centripetal force in this case? Yeah, thank you. So T sine theta equals mv squared over r. Now we have to remember that like this, the length of the chord is not our r in this case. Our r value is actually going to be this distance here, because this is the radius of the circle through which the ball is moving, right? So we want to be careful about this. And so what we would see then is after just taking the sine of theta, right, we see that we can just replace r here with L sine theta. Basically, just solve for r, right? It's a right triangle with base r and hypotenuse L. Okay, cool. So, I mean, it's just math at this point, right? And I'll get you started here, and then I'll let you just kind of take it to completion. And I'll definitely give you some like hints because the math here can get a little tricky. Let me do this. So we're going to say, right, that this equation tells me that T is mg over cosine theta. And this equation tells me that T is mv squared over L sine squared theta. So T being equal to T, of course, right, gives me, and I think we don't need the sketch anymore at this point, so I'll just bring this maximized. So we just write T equals T. And what we find is mg over cosine theta equals mv squared over L sine squared theta. And we can get rid of a factor of m here on both sides because it's common to both sides, so why not just cancel it? So we get rid of that. We get rid of that. And this is something that's going to be difficult to solve, right? And what we can do to solve this is we note that there's a trig identity that tells us sine squared of theta plus cosine squared of theta equals 1, right? And from this, we see that sine squared of theta is just 1 minus cosine squared theta. So we put that in here. And the last thing to do would be just notationally, right? If we define x, let me put this in words. Then what we find is that g over x equals v squared over L times 1 minus x squared. And note that this tells us that theta, right, we just do the arc cosine of both sides, that theta is arc cosine of x. And so what you would do here is you would just cross multiply, right? And you would want to turn this into a quadratic. Essentially, you want this to go like something like ax squared plus bx plus c equals 0, and then you just solve for x, right? You can do this with the quadratic formula, you can do it with the solver, you can do it with your calculator, however you want to do it. And that'll get you the answer. Is this clear to everybody? Are there any questions about this? Cool. Okay, so everybody feels good about going through and solving this at this point. And if not, just let me know. We can come back to it and try to take it a little bit further. All right, let's look at number 1 then. Somebody was asking about that. Let me bring that up real quick. This one, yeah. Okay. I will probably just put this on my other screen because I don't think I really need to do much drawing here. So let's do this. We have the mass. In my case, it is 3.6 kilograms. We have a coefficient of static friction. For me, it is 0.605. We have a coefficient of kinetic friction, which is 0.255. And we have some applied force, which is 13.1 newtons. And we want to kind of think about what happens. Okay, I mean, I'll probably just go through the whole thing. But we'll just talk conceptually kind of about what is going on here, and then write some stuff down. But so the idea is that whenever we have a problem like this, right, where there's a force being applied to an object that has a non-zero coefficient of friction, static friction in particular, between it and the surface on which it is resting, we want to see what the maximum static friction force could be, right? So in our case, we first determine the maximum value of the static friction force. Now we could write this maybe like this, and this is going to be just mu sub s times n, right? Because remember that static friction in general is defined as an inequality. And so this is just the maximum value of that. And then we compare this, right? We compare this to the applied force. And we want to keep in mind, like the question that we want to answer here is the applied force larger than the maximum friction force? And so let's say and ask, is the applied force larger in magnitude than the maximum static friction force? And so I probably won't go through and do the calculations here, but my feeling is that, just because I've seen lots of problems like this before, is that here what you're going to have is that this 13.1 newtons, or whatever number it is for you, is not going to be large enough to overcome the static friction force, right? So I suspect that this should just be 0. And if the applied force cannot overcome the static friction force, then the object will just not start, it will just never start moving, right? So I suspect that this is also, let's see here. Sorry, this shouldn't be 0. This should match the applied force. Because remember, right, it comes back to our general definition for the static friction force, which is the inequality, that it is the less than or equal to the static friction coefficient times the normal force, right? So this force, the static friction force, can match the applied force up to a certain value. And so, like I said, I think that this is what I would put. I would just put that it's 13.1 newtons and 0 here. Let's see if it likes that. Wait, what's up? Oh, we want to figure out the force that it's applying. I see. Okay, so it's this. So this should also be 13.1. If I'm not mistaken. Yeah. Okay. So then here, right, the idea is like probably for Bella, what you found was that the this force is larger than the maximum friction force, right? So what you have here is you just calculate the maximum static friction force at this point, which should be less than the external force. And then here, after t is no longer 0, you have to use the kinetic friction, right? So is that what you did, Bella, or was it something else? Or anybody, for that matter. Yeah, because you want to do static friction here, the maximum value of static friction here, and then you want to do kinetic friction here, right? Because this force is I'm assuming larger than the maximum static friction force. Does that make sense? Is everybody good with this? Cool. So if you're still struggling later, just let me know and we can come back to this and get you sorted out. Okay, so we looked at 1 and we looked at 6. Maybe no, sorry, we looked at 1 and 7, but 6 was one that, oh, I'm sick of this problem. Let's look at 8. This isn't so bad. I think this is actually a good problem. Okay, cool. So let me do this. Take a screenshot. Yeah, that's a good question to ask, right? And it very much does matter which angle you choose, right? Because the quadratic will give you, for number 7, right? The quadratic will give you 2 roots, and so you want to make sure that you're using the positive one because that's a physical one, right? The short answer is that it's the physical one. Cool. Okay, so what about this one here then? We want to do the same thing, right? We want to define our let's say our centripetal and y directions again. So I mean I'll just put this in because I think that this is exactly the same as the other one in essence, right? Because I mean the guy is to the right here, so we sort of know that the centripetal force must be pointing to the left, and so it would make sense that we identify our centripetal. No, I know. Yeah, I know it's showing it twice because I have the assignment open, and then I have the paint here where I'm actually drawing. So yeah, thank you for pointing that out though. But it is intentional. So these are going to be my xy axes, right? Or I should say my centripetal and my y-axes. Now, what are the forces that we have in these directions, right? Can somebody tell me? Let me do this. I'm going to zoom out a little bit here. Which one are we looking at? Is this number 8? Yeah. Okay, so number 8. What is, so my question for you then is, what is the centripetal force in this case? Because remember, we never just want to write like FC in our free body diagram. We want to be more specific than that. So somebody tell me. Yeah, the normal force. Great, thank you. So that is indeed what it is. It's really the only thing it could be. So I'll just try to draw that in as best I can. And it's going to, let's see. It's going to point like this. And so we see that this is actually like already perfectly aligned in the centripetal direction. We don't have to break it into components or anything like that. So cool. Let's write out our net force equation then. Remember that the net force in, I'll call it the centripetal direction, which is what we usually think of as the negative x direction in this case, is going to be the normal force. I'm not going to call it Fn, I'll just call it n. And this is m v squared over r, right? So that's cool. Now, what about the y direction, though? What forces do I have to think about in the y direction? So how do I fill this in? Yeah, so that'll be the gravitational force, right? So we could write negative mg. Now, that can't be all there is, though, right? Because the guy is not accelerating. Yeah, he's accelerating. Oh, is it? Oof. What about this? If I switch these, let's try that. That should be better, right? So yeah, friction going up, right, is what somebody said. And so we want to solve for the minimum coefficient, but we will think about the maximum friction force here, as I think I've said we usually can do. So why are you saying whoa? This is 0. So let me say this. Let me say max, just to be clear. So we can, you know, use the usual relationship, right? We use the usual relationship between friction and the normal force here. I'll just say still hold. And that is, remember that, oh, I see, yeah, okay. That the maximum friction force is equal to the coefficient times the normal force, right? And we already found the normal force because we wrote it for our centripetal force equation. And so remember that that was just found to be mv squared over r, right? And what we do then is we just solve this for the coefficient, right? So this equation here tells me that the coefficient is mv squared over rn, let's say. Wait, no, what did I just do? I messed this up. This should be mu sub s times this stuff. So let me just fix that. Mu sub s. Yeah, that's better. But wait a minute. Wait a minute. We need the coefficient. Oh, okay, I'm getting ahead of myself here because from this, or rather, we need to use both equations, is what I'm trying to say. We need to note that this one, right, suggests that mu sub s n must equal mg, and this one says that mu sub Sn equals mv equals mu sub s mv squared over r. So what we would do then is, I might actually just get rid of this because this is kind of what we want to focus on. Let me not get rid of it. Let me just continue writing here. Is that mu sub s, so we're kind of solving out of order here, right? But that's fine. Equals m v squared over big R, which is mg. And this just comes from using our centripetal force equation and our y equation, right? Just combining them, kind of like we did with linear dynamics, right? Linear Newton's laws. And we see that the mass ends up canceling out, which is great because we don't know what the mass is, right? We're not told what that is. So you can get the static friction coefficient from this relation here. Is this making sense? Is it clear to everybody? If there are any questions. Okay, cool. So there's that. Now, what is the other thing we need to do? Well, what we need to do is, like, once we have the static friction coefficient, then we can get the normal force, right? So this, yeah, it's a great question. I'll come back to that in a second. Let me just talk about what you do from this point, right? You want to solve this equation for the coefficient, and then you can solve this equation for the normal force, right? And you have to be careful here because they want the normal force in terms of the person's weight, right? And you should see that the normal force is basically just going to work out to be 1 over the coefficient of friction times the person's weight. So this factor is here essentially is just going to be 1 over the coefficient, if I'm not mistaken. Now, how I know the direction of friction is just by looking at all the other forces and then sort of using that to deduce which way the friction must point, because here the person is in contact with the surface, right? So there's a normal force. I think accept by now that whenever an object is in contact, I should say whenever an object is in contact and there's like some kind of acceleration, there has to be or some kind of motion, let's say generally, there has to be a normal force, right? And the gravitational force must point straight down, right? So if the person is going to stay suspended in that position, there has to be a vertical force to counteract the gravitational force, and that could only be friction, right? It kind of must be one of the forces that we've been working with so far, and there's only a couple of those. There's only, tension, normal force, gravitational force, and friction forces, right? So those are sort of the only valid choices for now when it comes into when it comes to when it comes to working with Newton's laws. And so you do have to convert the rotations per second to angular. No, you have to convert it to tangential velocity, or tangential speed, I should say. Now, you're the second person who said angular velocity. Is that what Hatridge is saying? Just out of curiosity, because like I said, you're the second person saying that. And it's not a huge deal, right? It's just that angular velocity is a bit different, to be pedantic. And we can talk about how you might do that. Let me see here. So we just want to get, I mean, there's a formula for this, right? Maybe we should just look at that. He's just saying velocity generally. Okay. Let me see if I can find this formula really quickly. I don't want to derive it. Honestly, I can if people are interested, but this is something we can talk about in more depth when we get to actual like angular kinematics and stuff. Let me see if this might be the way to go here. Well, I think that what we want to use is this, is V equals R omega, and I happen to know that omega is 2 pi f, right? 2 pi times the frequency. So you can just take this on faith for the time being, but what you would do is you would write, I'll just get rid of this because we didn't actually end up really using this. You would write that V equals R omega, which equals R. Now, yeah, this should be R 2 pi times the frequency. So this is what you're going to use for V. Now you should go through and do this, right, and check the units and make sure that it makes sense. It would be good practice for you. Well, like a good exercise for the reader, so to say. But I think that this is what you want to do. And we'll see where this comes from later when we talk about rotational stuff. But you could just take it on faith for the time being. Okay, cool. So that was a great question because it's definitely something you need to think about for this problem. But is this all clear? So to solve it without the angular velocity, you would just want to do like a dimensional analysis kind of thing, probably. And you would want to note that one revolution is essentially like this guy traveling the circumference of the circle, right? If you view this from the top. So one revolution corresponds to one circumference, let's say. And then you know, right, that the tangential speed must be well, you know that it must have dimensions of length over time or meters per second for the units, right? And so you can just sort of use the formula for circumference and the fact that this is just in essence something that has dimensions of inverse time, right? Because just to say this one more time, one revolution it corresponds to 2 pi times the radius, which is the circumference, right? So it seems like you should be able to just multiply this by 2 pi r to get the tangential speed. But I would say that that's a great thing for you to try on your own and work out, right? So, but we can also just do this. Okay, cool. Is everything clear so far then? Is there anything else I need to address for this one? I mean, the big thing here is just that they want it in terms of the weight. So remember that this is just mg. And I think this is a more suggestive way of writing it. So the last thing that I'll say then is just so what they want is what I would call like this fancy big N, right? Instead of the normal big N that I use for the normal force. And they want you to take the normal force that you find and divide it by mg. Okay. Cool. I think that then does it for this one. Are there any other... Let's see. What were the other homework questions people had? I think it was just like the last couple of problems, right? Let me see what else there are. Or 6 through 9, rather. Let's see where this one, 10. Well, look, right? When you solve for the normal force, you get something that is mg, or rather depends on mg, right? So if you divide by mg here, you would divide both sides by mg, basically. Now this side's going to go to 1, and that looks weird, but it's okay. And this side is going to give you what I wrote as that script n, which is what you actually are being asked to solve for here. But we can come back to that if it's still not clear after you like fight with it for a little bit, maybe. Okay, let's look at number 6. We'll just get this one out of the way. Now, we'll have to do a free body diagram here. I think that's there's no way sort of around that for this particular problem. So let me do my thing. Let me bring up my fancy image editing software here. So this is what we have. Now I would, of course, just draw the bear as a dot and the snowman as a dot, right? And these, the way that I'm going to imagine this is like I am standing so that the snowman is like coming right toward me. Or I'm sort of standing, right, there's a wall here where the shelf is mounted. I'm sort of standing with my shoulder against the wall and I'm looking straight down towards the bear. Because the perspective here has to be clear, or you're gonna wind up like with some weird like 3D system of vectors that's gonna be, you know, difficult to solve, right? So I would ask you what I should use for my centripetal and y directions, but it's going to be the same thing at this point, right? So we can just sort of forgo expressing that. So let's just draw the free body diagram. So the bear, right, will obviously have a gravitational force pointing straight down. Now, I'm not going to write m sub bear. I'm just going to write a big M because I think that that's easier. So the mass of the bear will be big M. So there's a gravitational force on the bear, right? There is a normal force on the bear, which we'll call big N. And then there is also a tension force on the bear, which should point like this. So is the perspective here clear to everybody? Like how I'm sort of imagining this? Okay, cool. So there's that, right? This is the bear. And then we do the same thing for the snowman. We're going to, of course, have a gravitational force pointing straight downward, and we can call this what they would call it, which is just little mg. And then there will be a normal force pointing up, right? Which I'll call little n, just to keep it separate from the big N. Now, this is where you come in, right? So like, what is the only other force that I need here for the snowman and the sled combination? It's the last thing I put in. Yeah, yeah, Chrisanne, if you're still there, it is your favorite streamer. Hi. Okay, so, yeah, tension, right? It's going to point to the left, like this. Well, there's no friction, right? Because the snowman and the sled are on an icy surface, right? So they tell us somewhere in the problem statement, where do they say it? Here, right? So you want to be careful not to put in forces that are not there. And the reason that it's fine that we have a force pointing to the left here, as I've drawn it at least, and nothing to sort of counteract it on the right, is because this is circular motion, right? This thing is going around in a circle. So we're fine with this, even though it seems a little weird. Does that make sense? Is that good? Because if you put friction here, you would be making this, I think, unsolvable. And we don't like doing that, right? Okay, so which one? What number is this? Number 6. All right. Now, I should just stop and say that I'm all about this problem because they don't give you any numbers, right? And I think at this point we all know that that's what I like. But I'd imagine that you're not so fond of that. All right, so I'll do the bear here, and then I'll have you help me do the snowman and sled. So we just do the usual thing, right? Nothing surprising about this at this point, probably. In the x direction, remember I'm taking my positive x direction to be pointing to the right, which is what we usually do. So I'm going to say that the tension, and again, I'm going to solve for the maximum static friction force here because that will just simplify things. And we just have to remember, which is easy in this case because they have us express our answer like this, but that we're going to actually wind up with an inequality because static friction is defined via an inequality, right? But we don't have to worry about that at all, really, right? So let me just say fs max, or wait, would this be, actually, hang on. You know what? Now that I think about this, I'm not so clear, or it's not so clear to me that we want to say it's the maximum static friction. Well, what else could we do though, right? Let's just do this, and I'll come back to that in a second. So this is 0, of course, because the bear is there, right? It's not moving to the right or to the left. It's stationary, so that's fine. And then we do the y direction for the bear. And this is going to be what? Big N minus big mg equals 0. And this, of course, tells us that big N equals big mg, right? Which, in turn, tells us that our maximum static friction force equals mu big mg. Okay? So hopefully that's all clear. Now, let's come to the snowman, and this is where I want your feedback, right? So what am I going to write for, like, the centripetal force on the snowman? What do we have here? Yeah, right, the same thing as before. Now, to be, yeah, let's just do this. T equals mv squared. Now, we want to write d here because that's what the radius is in this particular case, but exactly, should be v squared over the radius. Cool. So, I mean, this equation tells us that the tension, right, equals the maximum static friction force, which is mu big mg. And this equation then, right, if we just substitute in for the tension force, we have mu big mg equals m v squared over d. So the final thing to just remind you of is that when I set this up, right, I said that I'm not going to call the mass of the bear m sub bear because I think it's stupid to write a subscript that is an entire word. I just called it big M. So what we want to solve here is big M. And I think that you probably all see how to do that at this point, right? It's just a matter of dividing both sides by mu g. And that should be the answer that you put in. Does this all make sense? Is there anything unclear about this? Okay, nobody's saying anything, so I'll assume. All right, is it? I asked if there's anything unclear about it. You said no. Okay, so that means we're good. All right. Cool. Yeah, no, that's a good question. So the question is, why do we write D instead of L for the centripetal force expression? And that's just because, right, the only thing that's undergoing circular motion here is the snowman and the sled, and we can see from the sketch that the radius in this case is d, right? It's just the distance from the center of mass of this combined object to the point about which the circular motion is happening. So it's you know, it doesn't matter what we call it when it comes down to it, except for that the system will only accept U using D, right? It wouldn't accept R because that's not one of the choices. But interestingly enough, we note that this does not depend on big L, right? And it's kind of tricky that they would tell us express your answer in terms of all this stuff and big L, because we see that this doesn't end up being necessary. Cool. Okay. It seems like everybody's good with that. Then maybe we can look at one more here. Let's see. What was the other one people were asking about? Was it 9? I think it was 9, right? So let's do this. And this one is just going to really be about drawing a free body diagram for the car when it's at like the top of the first circle, and I guess at the bottom of the second one, right? So let's see here. Car travels down a straight country road that leads over hills and through valleys. Car encounters a hill that can be approximated as the top of the circle with radius this. Radius D. Yeah, so this is what we want to do here. We just want to draw the free body diagram for the car when it's at the top and bottom of these circles. So this one here, you know, there really won't be anything surprising about, I think, the free body diagram. It's more that like when we apply Newton's second law that we have some weird stuff happening. But what we would find here is just that there is a normal force. I'll call this, I don't know, big N. And then the gravitational force pointing down, right? And that's it. So what is my centripetal? So like, let me actually stop and first say that we're kind of thinking that like when the car is driving over the top of this bump here, it's sort of undergoing uniform circular motion, right? Because they tell us that the v is constant. Yeah, no problem, dude. I'll see you. They tell us that the v is constant. So then like what do we? Or actually, I think I said it. We have uniform circular motion here. So what do we do? It's not a trick question. It's like the same thing we've been doing all along, right? So number 9. Well, I mean, we have the gravitational force, right? So the strategy is just to apply Newton's second law. That's really what we want to do here. So we applying Newton's second law to the car when it's at the top of the bump. And let me swap these actually just so nothing is blocked. And this looks like this. I'll start this and then I'll just have one of you tell me what to do. And I'm going to say that in this case, like my negative y direction would be in my centripetal direction. So we have the normal force minus mg. Now, what do I write over here, right, to complete the statement of Newton's second law? What do I put? Yeah, ma, but it's a specific kind of acceleration, right? So we would want to write this. Yeah, thank you. So we write v squared over, and they call it r sub h, so that's what we'll call it. And the thing is that the apparent weight, right? This is not that different from say being on an elevator, right, as it's accelerating up or down and feeling, correspondingly heavier or lighter, right? So all we're going to do is we're just going to kind of imagine that there's like a scale uh, between the car and the road when it's at the top, say. And so we just identify the apparent weight with the normal force. And so what this would tell us, right, is that I'll write this one more time because we want to use the weight here, and mg is just the weight. This equals mv squared over r sub h. So we find, right, that the normal force is the weight plus mv squared over r sub h. Cool. Does that make sense? Is everybody good with that? Now it kind of seems like the other part of this problem. Can somebody tell me really quickly, or I can look, I guess. The other part is just asking about the apparent weight at the bottom. Yeah, so over here, which is essentially the same problem, right? So I will draw the free body diagram and let you work out the details, but it's going to be the same procedure essentially, because now we're thinking about the car. We're thinking about the car when it's here. And there is a normal force, which I'll call little n just to keep it notationally separate from the other n, the big N, right? Because these in general would be different. And then there's a gravitational force down again. So it kind of seems like the only thing that's changing here is the r value for our centripetal equation, right? So it's just the same exercise, but it seems like it's just going to involve a different r value. Is that clear? Does that make sense to everybody? Cool. Okay, I will probably end this here